G'day, it's Richard Marr from Marr's Classes again. Today we're continuing in the series of looking at how to interpret data and experiments. In this presentation we're going to have a look at a few terms: errors, uncertainty, precision and accuracy, what they mean, and how you can interpret them. So we'll begin by just having a look at the definitions of some of these terms. Now we often use the terms accuracy and precision in normal language and mean roughly the same thing, but in physics when we're taking measurements they will mean two different things. Accuracy is described as how close a measured value is to the actual or the true value, and precision is a term that we use to say how close measured values are to each other. So if we look at these targets at the bottom of this screen, we'll see that the person firing the arrows at the targets have had very different results. In the first one, they're all bunched together, but not near the bullseye. The second one, they're all bunched together near the bullseye, and the third one, they're spread all apart. So when we're looking at accuracy, we can see the first one, it is inaccurate. The second one is very accurate, and the third one is inaccurate. But when we're looking at precision, in terms of the definition we have above, we can see that the first one is actually quite precise, as is the second one, and the third one is imprecise. So when we're looking at those two terms, accuracy and precision, just recognise they have different meanings. And also, don't let precision fool you, because sometimes your measurements can have a bias. For example, if you're playing a game of soccer and you constantly, when you have a shot at goal, hit the left goal post, you're being very precise because you're hitting it regularly, but your accuracy is a bit off. A few other things with bias might be that when you measure something several times and the values all close, that bias may be built into your measuring instrument or in your measurement system, or the way you do it. For example, if you're using a spring balance and it constantly reads 1 gram, even when nothing's on there, you haven't zeroed that spring balance, so every reading is going to be out by a gram. If you, say, measured your height and you're always wearing thick-soled shoes, you're going to have that additional height of the sole when you're looking at your height. Or if you had a stopwatch that, even though once you click it, it takes half a second before the digital counter stops, that's going to be built in. So just be aware that just because all your readings are close together doesn't mean that they're going to be accurate. Now, just a word of warning, as I proceed through this presentation, it's going to be pretty dense with a lot of text, so I'd recommend that to follow it properly, you probably might have to pause the presentation every now and again to read through the information that I have. I'm going to give you an example now of when a group of students or a number of groups of students are working at measuring something, and it's a very simple measurement this time. It's just going to be measuring the length of an object. And when you look at all their data, you see that the 7 teams all got different results for the length of the object. Now that doesn't mean that they're sloppy, it just might mean that their measuring instrument or means of measuring isn't that accurate or precise, in fact. And if you look at the average lengths of the things there, they range from 2.65 up to 2.60 up to 2.8. The average length is 2.70 centimetres, that's the mean, by adding the 7 values together and dividing by 7. If you subtract the highest value from the lowest value, the difference between the highest and lowest values, or the range or the spread of values, is 0.2 of a centimetre, because as I said, it goes from 2.60 centimetres up to 2.80 centimetres. If you divide that range by 2, you get that half the range is 0.1 of a centimetre. Now we can use that as how far the maximum reading and the minimum reading are away from the average reading. So it's better when we're looking at all these results to express the length of this object, because there's 7 groups measured it, as 2.7 plus or minus 0.1 of a centimetre. Okay, so when we know that there's an error associated with every reading that we make, it's important to recognise that when we use that measurement, we have to take into account that error. So let's have a look at an example of a rectangle. So we're keeping these measurements very simple, we're just measuring length. If we put a rule along the length of this red rectangle, we see that the length is, well, it looks like about 51 millimetres, but it could be a little bit above, a little bit below. We don't really know 100%. So what we do is we're taking half of the smallest scale division. So if one scale division is 1 millimetre, half of that is 0.5 of a millimetre. So the length could be 50.5 millimetres or up to 51.5 millimetres. So we express that as 51 millimetres plus or minus 0.5 of a millimetre. When we look at the width of it, we see the same sort of thing. It's 31 millimeters plus or minus 0.5 of a millimeter. So that's all well and good when we're just measuring length. But what happens when we want to use those measurements of the length and the width of this thing to determine something like the perimeter of it? So we know that the length is 51 plus or minus 0.5, and we know that the width is 31 plus or minus 0.5. When we're looking at the perimeter, it could be as small as 30.5 plus 50.5 plus 30.5 plus 50.5. So it could be as small as 162 millimeters. Or it could be as large as 51.5 plus 31.5 plus 51.5 plus 31.5. It's 166 millimeters. So using what we did previously, the mean is 164 and half of the range is 2. So when we've added these together, what we've actually done, if you look at the errors there, the error in the length is 0.5, the error in one width is 0.5, and then the next length is 0.5, and the next width is 0.5. When we've added these measurements together, we've just added the absolute error together to give the overall error. 0.5 plus 0.5 plus 0.5 plus 0.5 is 2 millimeters. Okay, so when we add or subtract data, we just add the absolute error. But let's say we're not adding or subtracting. Say we're multiplying, for example, to determine the area of this rectangle. Now the area could be as small as 30.5 times 50.5, and that comes out to be 1,540.25 millimeters squared, or square millimeters. Or it could be as large as 51.5 times 31.5, and that's 1,622.25 millimeters, square millimeters, I should say. So the area, when we're looking at what it could be if we take the mean and half of the range, we get 1,581.25 plus or minus 41 square millimeters. Now that doesn't make any sense. So how can we give an area with precision down to 1/100th of a square millimeter when the error is telling us that we're not even sure how many tenths of a square millimeter there are? So more correctly, we should be expressing that area as 1,580 square millimeters plus or minus 40 square millimeters. So surely there's got to be an easier way to calculate and express this thing. So the way we do it, remember when we added or subtracted data, we just added the absolute errors. When we're multiplying or dividing data, we can't do that. So what we do is if we multiply and divide data, we can't just add the absolute errors. First you've got to convert those errors into percentage errors. So 51 plus or minus 0.5 is equivalent to 51 plus or minus 0.98%. And 31 plus or minus 0.5 is equivalent to 31 plus or minus 1.61%. Now when you multiply or divide data, you add the percentage errors. So in this case, we got 0.99% plus 1.61%. So we're multiplying 31 by 51. We add those percentage errors and it comes to 2.59%. Now if we look at what 2.59% is of 1,581, it's 40.9 square millimeters. So that's a way easier way of coming to that final value of 1,580 square millimeters plus or minus 40 square millimeters. Okay, so we've looked at accuracy and precision. We've looked at adding data and adding absolute errors, and we've looked at multiplying or dividing data and you add the percentage errors. Now let's have a look at how we can quantify this uncertainty, how it is we determine these errors. So what we did previously is we looked at the half of the smallest scale division. So it was measured to a millimeter. We said the error was plus or minus 0.5 of a millimeter. So that's all really, well, I mean, that makes a lot of sense, doesn't it? You're not sure. So in this example here, I've got 4.3 centimeters. It's not exactly 4.3 centimeters. It could be up to 4.35 or down to 4.25, somewhere in that range. So that sort of makes sense. But there's something that we haven't taken into account. And that is that if we're measuring something using a rule, there's going to be two ends that we're measuring, and either end is going to have an uncertainty associated with it, and the uncertainty at either end is going to be half of a scale division. So what we can do is make a general rule of thumb and say that in general we'll state the result of a reading as being the error of a reading as being plus or minus the smallest division on the measuring instrument. So that's just a rule of thumb we can use. So instead of saying 4.3 plus or minus 0.05 of a centimetre, we could easily say 4.3 plus or minus 0.1 of a centimetre, and that's a reasonable thing to do. For example, if we're using a stopwatch, when we're using a stopwatch that measures to 100th of a second, say we're looking at a pendulum going, and suppose the time is around about a second. If the smallest division on the watch is 100th of a second, that's about 1% of that 1 second, isn't it? So we could write that as 1 second plus or minus 0.01 of a second. So it's somewhere between 0.99 seconds and 1.01 seconds. Now that sounds pretty okay until you recognise that if you're using a stopwatch, the reaction time of the person will come into play. Now it might be, 0.15 seconds could be the reaction time between watching it start and watching it stop. So 0.15 seconds to start it, 0.15 seconds to stop it, meaning you're not accurate to 0.3 of a second. So overall, your 1 second could be out by 0.31 seconds. So it could be anywhere between 0.7 seconds and 1.3 seconds. So let's just go through conclusions from that discussion we've had there. If you accept the uncertainty, and sometimes called the indeterminacy, of about 1% for the measurement being made, if that's a reasonable sort of error, so a ruler marked in millimetres will be useful if you're measuring 10 centimetres or greater. Anything under that, that's going to be more than 1% error. And a manual operated stopwatch is useful for measuring times of about 30 seconds or more. If it's less than that, you're going to have some more accurate device. So when we do experiments, say for example, you might have done the one with the circular motion, we timed 20 revolutions, because that way it's going to be a lot more than 1 second, and the error, the percentage error, won't be as pronounced. Okay, let's now have a look at another concept with measurement, and that is significant figures. Now with significant figures, they're figures we write down in our measurement which say, yes, we have measured these. So a measurement of 1 centimetre, if we write 1 centimetre just with the unit, the number 1, and then followed by the unit centimetre, that's a different measurement to if we wrote 1.0 centimetres or 1.0000 centimetres. Because if you write 1.000 centimetres, you're saying I've measured it way down to 1,000th of a centimetre. So that gives an indication of the degree of precision in your measurement. So the rule of thumb with significant figures is, when you manipulate your data and say you multiply, divide, add, subtract your data, you can't have a final answer which has any more precision, in other words, any more significant figures than the least precise piece of data you have. So if your least precise bit of data only has 2 significant figures in it, your final answer cannot have any more than 2 significant figures in it. That's a nice, easy way of rounding and making sure that you're getting quite a reasonable result. Now I'm going to go back over error bars, because in a previous presentation I introduced them, but some people have indicated they're not too sure about what's going on there. With error bars, when we put a plotted point on a set of axes, we're saying that's where the measurement is. But when we now know that there's an error associated with that measurement, really the dot that we put on the graph is not, we're not sure of it. It's somewhere in that range there. I've drawn a little rectangle around these plotted points here, and that's an error rectangle, or in a previous presentation I drew an ellipse. What we're saying is that the measurement is somewhere within there. We don't know exactly where it is. Now error bars, you might think, well, all well and good, that helps me draw my lines of best fit and that sort of thing. But it will become important when you're looking at data, and a lot of people try and twist the truth by making data look like it's significant difference, when in fact when you include the error bars, you'll recognise that it's actually not a significant difference. So here's an example. We've got error bars there, and this is with enzyme activity in a controlled and treated. And when you look at it, the error bars do not overlap. So you're pretty safe in saying that the treated experiment had an impact. The control had a certain amount of activity, and the treated one had a certain amount of activity which is less. The error bars do not overlap. However, if you look at the second experiment, which is looking at the effect of a particular drug, it hasn't come up. If you're looking at the effect of a particular drug, You see, if we just put the dots in, you'd say, whoa, drug A is more effective than drug B. But once you include the error bars, you'll see really there's not that much significance. There's an overlap, and you don't know exactly where the data should be. In fact, this is a pretty lousy experiment, isn't it? Look at the accuracy of it. But I mean, that sort of thing happens a lot in advertising and so on. They'll present information in such a way that it makes you think that the data is showing something significant, but if they included the error bars, you'd recognise that it isn't. As I said in the previous presentation, I'm going to be trying to do a few presentations on experimental techniques throughout the year. And as I also previously said in this presentation, if you need to go back over anything, just rewind the video and pause it and have a look. And again, if there's any questions, please leave them below this video. So until next time, I'll leave it at that and see you